Okay, it's great to be with you, to be able to talk about climate change. I'm going to tell you a lot that you already know and maybe some things you don't know. And I'm going to start with the sort of basic background of how we got to where we are. You notice I have my jacket on. Okay, jackets don't carry warmth with them. All they do is hold the warmth of your body in. Another example of this is a car on a sunny day. If all the windows are rolled up, it gets warm, even if it's in the winter. That's because the energy of the sun comes in and can't get back out again, and it warms up the inside of the car. In our case, when we have a jacket on, it's the warmth that's within us that can't get out. So climate change is really like an, a down jacket around the whole planet. It's holding the heat in. What we've done to the atmosphere is holding the heat in and gradually making the planet get warmer. Now it's warm today, so I'm going to take this jacket off. But I wanted to make the point about what it is we're doing and how we're doing it. Now, uh, the issue, of course, is fossil fuels. And we always say the term fossil fuel and rarely stop to think about the word fossil. And what that means is it's literally like a fossil, like a dinosaur bone that's been in the earth underground for millions of years. It took millions of years to make this substance called oil and gas from uh, matter, dinosaurs, plant life, trees that were buried underground millions of years ago, tremendous pressure, and eventually the carbon coalesced into these fossil fuel substances. So, one important aspect of this is that we're now taking out of the earth carbon that has been underground for, as I say, millions of years. So when we take it out and burn it, and then the result of combustion is carbon dioxide, which goes up into the atmosphere. It's as if we're shoveling carbon out of the ground and throwing it up in the air. And the important thing is, it's been in the ground for all this time. It's been sequestered underground and therefore not part of the overall atmosphere of the earth. So when we burn fossil fuels, we're adding new millions of years old new carbon into the envelope that surrounds the earth. And by the way, the atmosphere of the earth is pretty fragile. Ed Muskie used to do a demonstration when he was working on the Clean Air Act, where he took a globe, like you used to have in your classroom, and it has a coat of shellac around it to make it sort of shiny and so fingerprints don't get on it. The point he made was the atmosphere of the Earth, in proportion to the size of the Earth, is about the same as that coat of shellac on that globe. It's very thin and it surrounds the earth. And as we're pulling the carbon out and burning it and turning it into carbon dioxide, it hangs around in the atmosphere. Carbon dioxide stays in the atmosphere a very long time, 100 years or more. And so, what this is doing is putting a down jacket around the earth and holding the heat in, which would otherwise radiate back out into space. And there's one other aspect of this that doesn't have anything to do with climate, but it does have to do with our use of this resource that we've discovered underground. And we're using it all up. It took millions of years to create the oil and gas that's under the earth. We're going to use it up in about 200 years. It's a finite resource. It's not being made anymore, or if it is, it's being made so slowly it won't help us. So it's an absolutely finite resource. And starting about 1850, we started to use this in a big way, which really accelerated at the beginning of the 20th century. And now we're using so much of it, we're taking it away from future generations in one sense. And then we're also getting that carbon out of the ground into the atmosphere. So, what does it do and why does it matter? And that's what I want to talk about basically today. That's what Kevin and Alan have asked me to talk about. Why does it matter to us and what's actually happening? Well, the first thing that's happening is it's getting warmer. This is average temperature starting at about 1880, early 1900s, down, up, down, up, down, up. But the trend is unmistakable starting around in the mid 30s. So, this is where we're headed. And the thing about the atmosphere and our ecosystem is it's delicate. People talk about how can 1 or 2 degrees Celsius really change things? It changes things a lot. Animal life, sea level, all of those things are sensitive to very small changes, which you may not notice. We may not notice day to day. It's a little warmer in the summer, and maybe ice goes out in the pond in March instead of April. But the changes in the overall system of the planet can be very substantial with a small change in temperature, and that's what's happening now. I talked about CO2. And a lot of times you hear people who deny climate change, they say it's all a hoax or it's normal cyclical. Well, no. Here's carbon dioxide in the atmosphere in the last 800 years. I'm sorry, 800,000 years. So almost a million years. And as you can see, it does vary. It pops up and down. There is a variability based upon things like volcanoes, the tilt of the earth, activity on the sun. There are lots of reasons that it varies, but the highest it's been in the last about million years was 300 parts per million. Remember that number, 300 parts per million. That was about 300,000 years ago. By the way, you can see it going. This is carbon dioxide. Way down here, this is about 15 or 20,000 years ago. We're going to talk about that. That was the last ice age. Okay, that's when it got really cold. Okay, here's where we are now. And it's happened in about 50 years. We've gone from around average 280 to 300 parts per million, 412 parts per million in 2020, and is still going up from there. So anybody that says, well, this is just a routine change, it's no big deal. The last time we were at this level was 3 million years ago. And the oceans, by the way, were 60 feet deeper. So this is new. This is new in human history. And carbon dioxide is the primary, in terms of volume, the primary greenhouse gas. But secondary to carbon dioxide is methane. And methane is a byproduct of natural gas. It's particularly a byproduct when you're pumping and drilling for natural gas. And methane, the problem is 80 times more of a down jacket than carbon dioxide. Methane is a much more potent greenhouse gas than carbon dioxide. Now, the good news is methane doesn't stay in the atmosphere as long as carbon dioxide, more like 20 or 30 years. And so if we can do something about methane, we can really make a difference in a fairly short period of time. Methane is the low-hanging fruit of combating climate change. And the oil and gas industry is getting there. They're doing a much better job in the recent years of controlling it, but it's something that we really have to pay attention to. You've probably heard about cows and methane. Cows burp methane. I always thought it was the other end of the cow, but apparently it's burping. But there's a lot of research going on about how to modify the diet of cows so that the methane, they don't expel so much methane into the atmosphere. But methane, the problem is, the reason it's of concern is, as I say, it's 80 times more dangerous in terms of a greenhouse gas. So who cares, Angus? What difference does it make? What difference does it make to us here in Maine? Well, I'm going to show you a chart now that really sort of grabbed my attention and talks about and explains why we need to be thinking about this. So why do we care about climate change? What difference does it make? What difference will it make in Maine? And what's all the to do about? Okay, so the temperature is going to go up a little bit, a few degrees. What's really going to change? Well, here's a chart that really got my attention and educated me to something that I really, frankly, wasn't aware of. This is, by the way, you can see the circle, my light right here, that circle. This is ocean depth over just the last 24,000 years, okay? This isn't millions of years or 800,000 years. This is 24,000 years, which is a period of time we can conceive of before the pyramids, but still, it's not a long period of time. So this is the depth of the ocean. 24,000 years ago, it was 390 feet shallower than it is today. In other words, you could walk to Peaks Island. Hell, you could walk to George's Banks. Look at a nautical chart. Anything in the Gulf of Maine that is shallower than 400 feet was dry land. It wasn't actually dry land. I'll get to that in a minute, but it was dry land. You could walk on. You could walk out there. So here's what happened. Now, why was the ocean so shallow 24,000 years ago? Because the water was locked up in the glaciers. This is the Ice Age. This is the last great Ice Age, and the water was in the glaciers, which, by the way, as we're standing here in Maine, 25,000 years ago, 2 miles thick of ice. 2 miles thick of ice from where we're standing, 2 miles in the sky. That's how much ice covered Maine and all of North America and most of Europe. So that's where all the water was. So as the water started to melt, not surprisingly, the ocean started to rise because the ice melted, the ice diminished in size, and the water the ocean level came up. Now here's a period that I think is scary. This is called the Meltwater Pulse 1A, and it occurred about 14,500 years ago, between 14 and 15,000 years ago. See how steeply the ocean rose during this period? If you do the math on this, it's about a foot a decade. The ocean rose a foot a decade. Every 10 years, the ocean would rise a foot. Okay? So that shows you what can happen. We tend to think of climate and climate change and changes in the weather and those kinds of things as gradual, millions of years. It'll take millions of years for these. No. In this case, the ocean went up 10 feet in 10 years. I'm sorry, 10 feet in 100 years, a foot a decade. So it can happen abruptly. I heard that word up at the University of Maine when I was talking to them about ice in Greenland. They talk about abrupt climate change, which frankly gave me kind of a start because I've always thought of this as such a gradual process. So we're going back 12,000, 10,000, about 8,000 years ago, and then something happens. The ice stops melting and the oceans level off. So for the past 8,000 years, sea level has been pretty much the same. Little minor variations, but pretty much the same. 8,000 years happens to be human history. So we think that the ocean is fixed. It's always the way it is. It's been this way when I was a kid, and it's going to be that way, and it was a way when my grandfather was a kid. So 8,000 years, it's been static. And it's sort of lulled us into an assumption that it's always going to be the way it is, and it always should be the way it is. The problem is that's not true. Because what we're experiencing now, because of the weather getting warmer and the seasons getting warmer, is the remainders of the glaciers are melting. Greenland is melting at a record rate. I went to Greenland 4 or 5 years ago. It really made me a believer. When you see the water across the ice cap, we took a helicopter out over the ice cap in Greenland, and you can see what looks like the Kennebec River flowing along the top of the ice and then down into a deep hole called a moulin that goes down miles through the ice cap and lubricates the bottom and helps the ice to move out and turn into icebergs and go out into the ocean. Greenland is melting at a record rate. There's about 20 feet of sea level rise just in Greenland. There's 212 feet of sea level rise in Antarctica. 212 feet of sea level rise in Antarctica. And then, of course, there are glaciers around the world, which are all retreating. There are places now where it used to be parks based upon the glaciers that have signs that say formerly Glacier National Park or formerly, because the glaciers are retreating. It's obvious. Again, I saw a glacier up in Greenland that had retreated as much in the last like 10 or 15 years as in the prior 150 years. So it's an accelerating process. And as that process goes on, sea level rises. The other reason sea level rises, I never knew this before, is that warmer water is bigger than colder water. The warmer water expands slightly, but when you're talking about something the size of the ocean, it's a lot. So the combination of warmer water, which expands, and the melting of the ice around the world is leading to sea level rise. Now, there are a lot of discussion and debates about how much it will be and how long it will take. Every I've been following this now for 15 or 20 years. Every estimate that I've seen, it always gets worse 4 or 5 years later when they have new data. And the most recent estimate I've seen from a reputable climate scientist is about 6 feet of sea level rise between now and the end of this century. That's 70 years. You know, that's like us going back to the 50s. That's that's a conceivable time period. And 6 to 10 feet of sea level rise in that period will be catastrophic. It'll be catastrophic because, well, Scarborough Marsh, goodbye. Any place in Maine that's low lying, that isn't rocky shore, is going to have a real serious problem just because of the sea level. But then when the sea level rises and you have a storm, it compounds the problem. Miami, New Orleans, New York, Bangladesh, any coastal city, Singapore, it's going to be an enormous change that we're going to have to cope with. And the cost of coping with it, by the way, is going to be astronomical. People talk about the cost of doing something about climate change now. It's going to be dwarfed by the cost of seawalls and rebuilding roads and mitigation over the next 50 to 100 years. So this is a case where a little prevention could very well go a long way. Now, there are other problems. I wanted to focus, you know, we could talk all day about this, and I wanted to focus on sea level rise, but uh, there are other issues that are related to this. Two that I'll mention. One is ocean currents. You don't read much about that, but ocean currents are very mysterious. These rivers of energy that flow. The Gulf Stream is the best known, that goes up the east coast of the United States, turns right, goes up, and the Gulf Stream makes England and Scandinavia habitable. The energy from the Gulf Stream makes those places habitable. We think of England as being east of us. They're really quite far north of us. England is the same latitude as Hudson Bay, and Hudson Bay is a pretty inhospitable place to live. So if the ocean currents change, then you have dramatic changes in the climate of significant areas of the world. And I just picked on the Gulf Stream as one example. The other problem, and after this I'm going to try to get to some solutions. The other problem is national security. As I'm recording this, we're talking about a crisis at the southern border. And over the last several years, we've seen a refugee crisis in Europe, both from Ukraine and earlier from Syria. And we all know what the impact of those Syrian refugees was in Europe. It turned the politics of Europe upside down. There were about 6 million Syrian refugees. The estimate for refugees from climate, from the tropical belt around the world that's going to become, I wouldn't say uninhabitable, but very, very difficult, is between 100 and 200 million people on the move. That's a national security issue. That's a humanitarian issue. It's not only heat, but it's drought, famine, and all the reasons that people have moved in large numbers throughout history. I don't think, frankly, any of us, in terms of America or the Europeans, are really adequately thinking about what the implications of this, if indeed it comes to pass, and it's already starting to come to pass. Some of the people coming to the southern border are climate refugees. And it's something that we're going to have to address. I don't know what the answer is, except the point I want to make is this is a real life consequence of what we're talking about. This isn't ice out early on Great Pond. This is a serious infrastructure problem, and also, I believe, a serious national security problem. Now, okay, Angus, you painted a pretty dark picture. Uh, what do we do? What happens? What do we have to do to solve this? Well, the shortest answer is stop releasing CO2 into the atmosphere and methane. Methane we can control in many ways. It's not entirely, of course, but methane is a as I mentioned, the low-hanging fruit. The technology is there to control and capture methane. CO2 is more difficult. Where does CO2 come from? Well, basically, it's in three buckets, three areas. One is energy generation, power plants burning fossil fuel, whether it's coal, oil, natural gas. The second part of where CO2 comes from is transportation, automobiles, trucks, also burning fossil fuels. The third area is industrial and space heat, heating your house, heating buildings, heating factories, baking, uh, running factories to manufacture things. So those are the three areas. Okay, what do we do about this? Well, we stop burning fossil fuels. That's a start, but that's not going to be an easy transition. Some of my environmental friends say, well, no more fossil fuels, no more pipelines, just shut it off. Well, the problem is we've got a long way to go before we have a renewable uh, basis of our energy that's sufficient to meet the demand that we already have. People want the lights to come on when they flip the switch. Well, okay, I just want to put this in perspective for you. In New England today, about 60% of our energy comes from natural gas. Okay? 60% comes from natural gas, none of which, by the way, comes from New England. It all comes through pipelines. And then we have a little nuclear in the mix in New England, and then we have renewables, hydro, biomass, uh, wind, solar. Okay? It's about 10% of our energy mix in New England. So, for starters, if you say let's have 100% renewable power, it means 10 times the amount, the number of renewable power developments, whether it's solar, wind, whatever, 10 times what we have now, and that's not going to be easy. That's a major change in infrastructure. Even if we could just wave a wand and do it, it would take years to develop and build those projects and to get the permits. And I'm going to talk about that in a minute. And to get to the permits for those projects. So if people talk about a renewable future, they've got to recognize and be clear-eyed that this means a lot more solar farms, a lot more windmills, and probably a new generation of nuclear plants, which I know people are uneasy about, but nuclear is a fossil-free energy source, and if we can deal with the waste and figure out how to do it, and there's a lot of talk about modular nuclear reactors, when that if we can have a breakthrough in that area, that could be the long-term solution, but we can't hope and wait for the technology to develop. Now, here's the problem with the major renewables, wind and solar. The wind doesn't always blow and the sun doesn't always shine. The term for them is intermittent resources. In other words, they make a lot of power when the wind's blowing, when the sun's shining, everything's great. The problem is, what if it's a windless night? The windmills aren't turning, the solar power isn't making any power. What do you do then? People still want to turn the lights on. The big gap right now, I believe, the big obstacle between us and a renewable energy future is storage. How do we would build more, we would overbuild the capacity for the renewable capacity. And then when it was producing, real windy day, real sunny day, put part of that power, put most of it in the grid, but put part of it into storage somewhere. And then when it's dark at night and the wind's not blowing, you pull that power out, and that gives you 24-hour, 365-day power. The problem is we don't have the current technology to do that cost effectively. Everybody's working on it. It's one of the major things that I've been working on in Washington is funding research into energy storage. And batteries is the obvious one, but batteries take rare earths and special kind of minerals and all of those kinds of things that raise a whole separate set of problems. I'll talk about that in a minute. But so batteries is one. There's an old technology called pump storage, which you take a body of water and you have another body of water up at the top of the hill. And when you have extra energy, you pump the water up the hill. And when you need the energy, you let the water run back down through the turbines, and it handles your backup. It's a kind of storage system that goes back 100 years. People are experimenting with all kinds of other technologies, molten salt and flywheels and everything else. But storage is the big deal. Storage is the real Green New Deal. That's what will make the difference and allow us to go to renewables as a baseload power source. Now, having said all that, here's the problem. It takes too long to get these things done. Remember I mentioned pump storage? We had testimony at the Energy and Natural Resources Committee not too long ago that the length of time it takes to permit a pump storage project in the United States today is around 17 years. The amount of time it takes to permit a hydro project, 10 to 15 years. And by the way, millions of dollars. Wind and solar. And the other big piece of this is transmission. Getting the power from where it's generated, from where there's a lot of wind, say Nebraska, to Chicago or to Denver. Getting the renewable power from where it's generated to where it's needed is going to require a lot of new transmission lines. The estimate I've seen is 2 to 3 times the size of the current grid. So that means, remember, if the goal is a renewable energy future, we're going to have to figure out how to build more transmission lines and how to take some of the minerals out of the ground that we need for electrification. And that's part of the cost of getting there. There's no free lunch in energy. I've learned that over 30 years. Everything has an impact. But this is what we have to really think about as we move into this transition period. It's not going to be easy. And that's one of the reasons in Washington I'm working with Joe Manchin and a bunch of Republicans, everybody I can find, on permitting reform, not to change the standards. This is important. Not to lower the environmental standards, but to make it more timely and predictable. Deadlines. We don't have time. We're in a race with climate change. We don't have time to spend 15 or 20 years trying to get some necessary project that done to help us into a fossil-free future. I mentioned electric generation, transportation, same deal. Electric cars. You can't love electric cars and hate lithium mines, because the batteries of almost all electric cars are based upon lithium. You know where 87% of the processed lithium comes from that we use today? China. China. Talk about a national security problem. There it is. We move forward and people are buying electric cars like crazy. They're going up very significantly, and that's a good thing. But we have to realize that it's not a good idea to be dependent for a critical mineral on a country that I wouldn't call an adversary, but I'd call a pretty active competitor who doesn't necessarily wish us well. And the Europeans learned how dangerous it was to be dependent upon Vladimir Putin and Russia for natural gas. And I think the same goes for lithium and other rare earth minerals that the Chinese are busy gobbling up around the world, gaining control of in Africa, in Congo, in places all over the world. They are cornering the market on many of these minerals that are necessary for battery technology and other technologies of the 21st century. So energy storage, to me, the two big issues are energy storage and permitting reform, so we can get the work done that's necessary to get to a fossil-free future. And again, I want to emphasize, when I say permitting reform, I'm not saying lower the standards. When I was governor, I used to say, I want Maine to have the toughest environmental standards in the country and the most timely and predictable environmental permitting process. And that's really what we have to strive for, not to lower the standards, but to streamline. I hate to use that word streamline, that's become a euphemism for gut. I don't mean that at all. To make the permitting process have some real deadlines and a predictable time frame. And I think that's one of the most important things that we can do right now to get where we want to get. Because remember the carbon budget, power, transportation, space heat. If we can decarbonize power and electrify transportation, you've dealt with 2/3 of the problem. And then you get to things like electric heat pumps, and you're up to 70, 80, 85% of the problem. So the solution is in front of us, but it's not going to be easy. And I've been involved in environmental matters as long as I can remember, but the sort of instinct of the environmental community has always been to say no. And we got to start saying yes, understanding that we may have to accept a small unit of a small amount of environmental loss to get a huge amount of environmental gain. If you have 100 units of environmental gain and 8 units of environmental loss, that's a deal that we have to make. It can't be done without any impact. It would be nice if it could, but you can't put electricity in a FedEx box and send it across the across the country. It's going to have to be transmission. Now, what can you do? What can businesses do about this? Well, for one thing, just understand how important it is. And don't fall for this stuff about, oh, this isn't a big deal and it's just cyclical and it'll go away and it's sunspots and those kinds of things. This is a serious problem and it has to be dealt with seriously. You can also, in your own business, in your own community, make change that will help us move in that direction, like Geiger Brothers up in Lewiston that have built a solar plant, and Chinbro up in Pittsfield. Now, you may not be a big enough company to build your own great big solar farm, but there are ways that you can join together and do community solar, and also just understand and communicate with your fellows, your people that you work for you and with you, how important this is. And it's going to be based upon, in many ways, the solution will be based upon millions of individual decisions. And that's really how change happens, is when people start to make individual decisions. And I believe the change it'll be disruptive, but it won't be destructive. It will be disruptive, but it shouldn't be destructive if we think it through and deal with it in a serious and thoughtful and comprehensive way. We can make a difference. This is one of the most, well, it's certainly the most serious environmental issue that the human race has ever faced. And we have an obligation to face it and do something about it. We have an obligation because we have the planet on loan. I'll end with something that I've said on the Senate floor. All you need to know about environmental policy is what I call the Maine rototiller rule. I used to borrow rototiller from Peter Cox. When you borrow somebody's rototiller, you return it to them in as good shape as you got it, and if you can, with a full tank of gas. That's really what we have to talk about, because we have to understand that we have the planet on loan. We don't own it. We may own pieces of it for a lifetime, which isn't very long when you're talking thousands of years, but we have it on loan from future generations. And we have an obligation to the people that we're borrowing it from to give it back to them in as good a shape as it was given to us. Probably better, now that we understand the magnitude and the significance and the causes and the solutions to this problem. So I'm glad to be able to be with you today, and you can see my light right there. Anyway, it's great to be with you. I appreciate your interest in this topic. Sorry I've talked so long, but it's a big topic, and I look forward to seeing you, working with you, and finding solutions for our communities, for Maine, for the United States of America, and for the world. Great to be with you. See you later.